Okay, let's jump right in. Today, we're tackling a truly fundamental building block in computer science, something really essential for organizing information efficiently: the binary search tree. If you've ever wondered how systems manage, huge amounts of data so you can find things fast or add or remove stuff quickly, well, this is a big part of the answer.
That's right. We're going to take a deep dive specifically into the binary search tree, often just called a BST. And we're using excerpts from Hello Algo as our guide today. It's a structure that looks pretty simple on the surface, but it holds a really powerful secret for keeping data sorted and accessible.
And our goal for you, the listener, is to cut through the technical jargon. We want to really unpack what makes this structure tick. We'll explore its core rules, see exactly how the key operations work, and understand why it's so incredibly useful in practice. By the end, you should have a solid, memorable grasp of the binary search tree. Okay, let's unpack this.
So at its core, a binary search tree starts as a type of binary tree. That just means each node within the tree can have, well, at most two branches or children coming off it. We usually call them the left child and the right child.
Simple enough, but it's not just any old binary tree, is it? There's a crucial rule it follows.
Exactly, that's the key. The defining feature, as the source lays out, is a specific ordering property. It has to hold true everywhere in the tree. There are basically two conditions.
Okay.
First, for any node you pick starting with the root, the very top one, all the values in its entire left subtree. So every single node you can reach by going left must be less than the value of that node itself.
Okay, so everything on the left side of a node is smaller than the node. Got it.
Precisely. And the second condition is just the mirror image. For that same node, all the values in its entire right subtree must be greater than the value of that node.
Got it. Left is less, right is greater. Seems straightforward enough, at least for one node.
It does. But here's the real magic, and what the source emphasizes is crucial. This property is recursive.
Recursive meaning?
Meaning it doesn't just apply at the root. It applies to every single node in the tree, all the way down. Every subtree, no matter how small, is also a binary search tree following these same rules.
Okay. And why is that recursive thing so powerful?
Because it creates this incredibly organized landscape, you see. When you're looking for something or trying to find the right place to put something new, this recursive ordering means that at any node, you instantly know which way to go left or right to narrow things down. It's kind of the secret sauce that makes it fast.
Okay. So that structure lets you really zero in. So with this organized tree, how do we actually, put it to work? The source walks through the fundamental things you do: searching for data, adding new data, and taking data out.
Right. The Hello Algo source presents the BST, typically managed as a class. Mostly, you just need to keep track of the root node that's your entry point to the whole tree. Let's go through the operations one by one.
Okay.
First up, searching for a node with a specific value, let's call the value num. You always start at the root node.
Okay, so it's like navigating a map where every junction tells you exactly which of two roads gets you closer.
That's a great analogy. You compare the value you're looking for, num, with the value of the node you're currently at. Let's call it cur.val. Now, because of that BST rule, if the current node's value is less than the target value, cur.valNum, where does that recursive property tell you the target must be if it's in the tree at all?
It has to be somewhere in the right subtree, right? Because everything on the left is smaller, so you'd move to the right child.
Exactly. You update your current position, cur.right, and cur.right. And conversely, if the current node's value is greater than the target, cur.valnum, where do you go?
Left.cur. Cur.left.
And if cur.val happens to equal num?
You found it. Done.
Precisely. Search over. Now, if you keep following these comparisons, moving left or right, and you eventually hit a point where the direction you need to go leads to like an empty spot represented as none or null PTR in code maybe, and you haven't found num yet, then you know the value simply isn't in the tree.
This feels incredibly efficient. You're constantly discarding a huge chunk of the tree with each comparison. It sounds really similar to the classic binary search algorithm we use on, like, sorted arrays or lists.
It is the same fundamental idea, yeah, just applied to a tree structure. The source correctly points out this connection. By making just one comparison, you eliminate roughly half of the remaining nodes you might have to look at.
And that efficiency translates into, what is the time complexity again?
For searching in a balanced BST, and we'll talk more about balance soon, it takes O log n time. N is the number of nodes.
O log n.
Yeah, think about it. Searching in a tree with 1,000,000 nodes might take around 20 steps. Log base 2 of 1,000,000 is roughly 20. Compare that to potentially a million steps in an unsorted list. And it's a massive win for speed and practice.
Oh, well, again,
Yeah.
that's a key takeaway right there.
Yeah.
Okay, second operation, inserting a node. You want to add a new value, but you absolutely must keep that left-right rule intact everywhere.
Right, so the process for finding the location where it should go is almost identical to searching. You start at the root with the value you want to insert, num.
And you compare going left if the current node is greater than num, and right if it's less, just like searching.
That's exactly right. You traverse down the tree, following that left-right rule based on num compared to the current node's value. You keep going until you reach a point where the next step, left or right, would lead into an empty slot, a none or null PTR.
And that empty slot is the correct place to attach the new node.
Exactly. That's where it belongs to maintain the order. You create a new node containing num and link it right there. The source mentions a couple of important practical details here.
Oh, yeah.
First, standard BSTs usually don't allow duplicate values. If you try to insert a value that's already there, the insertion typically just stops or maybe throws an error. Depends on the implementation.
Makes sense. Duplicates would mess with the strict ordering rule. What's the second point?
To actually make that connection when you find the none spot, you need to know which node should be the parent of this new node you're adding.
Oh, right. How do you know that?
Well, the code examples in the source often show using another variable, maybe called pre for previous, to keep track of the node you were just at before you tried to move into that empty slot. That pre node is the parent. Then you just update its left or right pointer to point to your newly created node.
Okay, so you trace the path down, remember the last real node you visited, and tell that node, hey, connect to this new one. Clever. And insertion efficiency. Still fast.
Just like search. Because
Yeah.
you're basically just traversing a path down the tree. Insertion also takes O log n time in a balanced BST. Again, adding an item even to a huge tree is very quick.
Okay, search and insert seem manageable. You're just following rules or filling an empty spot. Removing a node, though, especially one that has children, that sounds like where things could get tricky. How do you take something out without messing up the whole tree's structure and that left root right property for everyone else?
You're right, removing is the most complex one. Because maintaining that core BST property is absolutely key. The source breaks it down nicely into cases based on how many children the node you want to remove actually has.
Okay, cases.
Let's hear them.
Case 1. The node has 0 children. It's a leaf node, right at the bottom.
The easiest one.
Yep, the easiest. You find the node. Then you just need to tell its parent node to forget about it. You set the parent's left or right pointer, whichever was pointing to the leaf, to none or null PTR. Poof, it's gone. The source has figures showing this concept.
Just trim the leaf.
Yeah.
Simple enough. Okay, case 2.
Case 2. The node has exactly 1 child. Could be a left child or right child. You find the node. In this situation, you can effectively replace the node you're removing with its single child. So you update the parent of the node to be removed. Tell it to point directly to the grandchild node instead. Basically, you bypass the node you're deleting. The child steps up into its parent's place in the structure.
Okay, that makes sense too. Promote the single child. Still seems logical. Now for the big one. Case 3. The node to be removed has 2 children.
Ah, yeah. This is the tricky one. You can't just remove it because what happens to its 2 subtrees? And you can't just promote, say, the left child, because then what about the right child? It might violate the rule for the nodes over there.
Exactly. This is where we need a more clever strategy to keep the BST property intact for the whole tree. And the source explains this really neat technique. Instead of removing the node itself directly, you find a different node somewhere else in the tree whose value can legally replace the value in the node you want to get rid of. Then you remove that other node instead. And the trick is, that other node will always fall into one of the simpler cases, case 1 or case 2.
Whoa, okay. You swap the value? Kind of. But which node has the right value to borrow?
Good question. You need a value that fits perfectly between the left subtree and the right subtree of the node you're removing. The source suggests using the node with the smallest value in the right subtree of the node you want to remove. This node has a special name. It's called the in-order successor. If you listed all the nodes in sorted order, this successor is the one that comes immediately after the node you're trying to remove.
The smallest node in the right subtree. How do you find that?
It's a specific path. Starting from the node you want to remove, you first take one step to its right child. From there, according to the source, you just keep following the left child pointers as far down as you can possibly go. Keep going left, left, left. The node you end up at the one that has no more left children in that specific path that's your smallest node in the right subtree. That's the in-order successor. The source code might call it TMP.
Okay. Go right once, then left, left, left until you stop.
Yeah.
Got it. So now you've identified the node to remove, sure, and its in-order successor, TMP. What's the next step?
You take the value from the successor node, tmp.fullval, and you copy it into the node you originally wanted to remove, cur.vol.
Ah, so you overwrite the value in cur.
Exactly. Now, the node at cur holds a value that correctly fits between its original left subtree, which is smaller, and its original right subtree, which is larger. It satisfies the BST property at that spot.
But wait, the successor node, TM, the one you copied the value from, it's still physically sitting there in the tree, right? With the duplicate value now.
It is. But here's the elegant part. Think about that in-order successor, TMP. It was the smallest value in the right subtree. By definition, it cannot have a left child.
Why not?
Because if it did have a left child, that child would have an even smaller value, and it would have been the smallest one you found by going left.
Ah, right. Okay, so the successor node, TMP, always falls into case 1, no children. Or case 2, it might have a right child, but definitely no left child.
Precisely. It will always have either 0 or 1 child, or right child, which means you can now remove the successor node, TMP, using the much simpler case 1 or case 2 logic we already discussed. The source mentions you can effectively just call the remove function recursively on tamp's value to handle its actual deletion cleanly.
Wow. Okay, that is a clever dance. You replace the value at the difficult spot to maintain the structure. Then you remove the node you copied from, which is now guaranteed to be an easy removal case. It feels a bit roundabout, but it totally works and keeps the tree valid.
It's a classic, elegant solution. And importantly, like search and insert, the overall time complexity for removal, even this complex case, in a balanced tree is still O log n. That includes the time to find the node, find the successor, which is just another path down the tree, copy the value, and perform the final simple removal. So all the core operations are efficient.
Okay, that covers managing the tree. What else makes BST special?
Well, beyond just searching and manipulating, the very structure of the BST leads to another really useful property. It relates to how you visit every node, which we call traversal.
Right, traversing the tree. I remember there are different ways, like pre-order, post-order.
Yes, and the source specifically highlights in-order traversal for BSTs. Remember the rule for in-order?
Visit left subtree, then the node itself, then the right subtree.
Exactly. Visit the entire left subtree first, then process the current node, the root of whatever subtree you're looking at, and then visit the entire right subtree, left decker right.
Okay, and how does that connect back to the BST property of left root right?
It's a direct consequence, because all values in the left subtree are smaller than the root, and all values in the right subtree are larger. When you follow that in-order sequence processing all the smaller values first, left subtree, then the root's value, then all the larger values, right subtree, you are inherently visiting the nodes in ascending order of their values, sorted order.
Wait, really? So just doing an in-order traversal on a BST automatically spits out a sorted list of all the elements in the tree.
Yeah.
That's actually a huge bonus.
It absolutely is. The source calls this an important property. The sequence of in-order traversal in a binary search tree is always ascending. You get your data sorted basically for free, just by walking the tree in that specific way.
That's very cool. What's the cost to get that sorted list, though? It can't be O log n, right?
No, because you have to visit every single node in the tree to get the full list. So the time complexity for an in-order traversal is O(n), where n is the number of nodes. You touch everything once. But, as the source points out, getting a sorted list this way is often way more efficient than, say, dumping all the data into an unsorted list and then running a completely separate sorting algorithm like quicksort or merge sort on it.
Right. So you build this efficient structure with O log n, search, insert, delete, and you get this O long sorted output essentially as a side effect of the structure itself. Pretty good deal. Okay, we've talked O log n and O(n). Let's zoom out a bit. How does this O log n performance really stack up against, I don't know, a much simpler way of storing data, like just using a basic array?
Yeah, the source gives a helpful comparison table, basically. Let's look at the key operations. For searching, in an unsorted array, worst case, you might have to check every single item. That's OIMN. In a BST, as we said, it's O log n. For large data sets, that's the difference between maybe milliseconds and potentially minutes or hours. Huge win for BST on search.
Okay, search is clear. What about inserting?
For inserting, Adding to an unsorted array can actually be super fast. O1, if you just tack the new item onto the very end. Inserting into a BST we know is O log n, so the simple array can be faster just for adding things to the end.
Okay, and removing.
For removing from an unsorted array is slow again. First, you have to find the item, which is O long. Then, if you want to close the gap left behind, you might have to shift a bunch of other elements over, which could be another ON operation. So removal is generally ON, removing from a BST O log n.
So BSTs totally dominate for searching and removing, offering that O log n speed versus the array's ON. Insertion is O log n for BST versus maybe O1, best case for the array, but O log n is still pretty fast. It really seems like if you're doing a lot of searching or deleting, or both, the BST is the clear winner.
That's the key takeaway the source emphasizes. BST operations are described as stable and efficient. They're especially good when lookups and removals are common things you need to do. Unsorted arrays really only win out if you're mostly just adding items and you almost never need to search for or delete specific ones.
You kept putting that little asterisk next to O log n efficiency. You kept saying in a balanced BST. What happens if the tree isn't balanced? What does that even mean?
Ah, yes, this is the critical caveat, the potential downside. That amazing O log n performance relies entirely on the tree having a height that's roughly proportional to the logarithm of the number of nodes. Think of a tree that spreads out, kind of bushy as it gets taller. That's balanced. But as the source illustrates conceptually, think like figure 723 in the text, if you insert nodes in a very specific unlucky order, like say you insert numbers in strictly increasing order, 1, then 2, then 3, then 4.
What happens?
Well, 2 is greater than 1, so it goes right. 3 is greater than 1 and 2, so it goes right again. 4 goes right again. The tree doesn't branch out, it becomes skewed.
Skewed, like lopsided.
Even worse. In the most extreme case, it can completely degenerate into a structure that looks exactly like a linked list, just a single long chain where each node only has a right child, or only a left child if you insert it in decreasing order. In that worst-case scenario, the height of the tree is no longer related to log n. The height becomes proportional to n, the total number of nodes.
Oh, no. And if the height is effectively n,
then the time it takes to traverse from the root down to the furthest node isn't O log n anymore, it's O ln, which means all those operations we were celebrating, insert, remove, they all degrade to O on time complexity in the worst case. Because you might literally have to walk down that entire chain, checking every single node. You completely lose the main performance advantage of using a BST.
Wow. Okay, so the incredible speed of a BST is conditional. It relies on the tree staying reasonably balanced.
Absolutely. Maintaining balance, or at least avoiding severe imbalance, is absolutely key to getting that O log n efficiency in practice.
Okay. So despite that potential pitfall, which sounds pretty serious, BSTs are clearly powerful when they are balanced or managed well. Where might we actually encounter these structures being used out there in the real world? The source lists a few application areas.
Yeah, they pop up in quite a few places where you need data kept in order and searchable efficiently. One very common use is as multi-level indexes in various systems. Think about databases or even file systems on your computer. BST-like structures can help organize pointers to beta blocks or records hierarchically, so the system can quickly locate the specific piece of data you need without having to scan through everything linearly.
Okay, like an index in the back of a book, but multi-layered and faster.
Exactly. They're also sometimes used as the underlying structure for certain search algorithms themselves. They provide that efficient framework for the lookup part. And the source also mentions using them for storing data streams while keeping everything sorted on the fly. Imagine data is constantly arriving, maybe sensor readings or stock prices. You can insert each new piece into a BST efficiently using that O log n insert. And because the tree keeps everything ordered, at any moment you can very quickly find the minimum or maximum value currently in the stream, or pull out all the data within a specific range.
Right, because it's always maintained in that sorted structure. So bringing it all together, what does understanding all this really mean for you, the listener, just using your computer or phone?
Well, it gives you some insight into the fundamental engineering choices made behind the scenes in the software you use every day. When you search for a contact or look up a product online, or maybe even when the operating system saves a file, there's often a clever data structure, maybe not exactly the simple BST, but something based on it, working hard in the background. It's applying these simple recursive rules, left is less, right is greater, to make sure those operations happen fast, even when dealing with, huge amounts of information.
Yeah, it really highlights how applying relatively simple, consistent rules at a fundamental level can lead to really powerful and efficient solutions for managing data in our digital world.
Mm-hmm.
It's not just magic. So we've taken a pretty thorough deep dive into the binary search tree today, using Hello Algo as our map. We covered its defining property, that recursive left-less right-greater rule. We walked through the mechanics of searching, inserting, and that multi-case logic for removing nodes, including that clever successor swap trick. We discovered the need side benefit. Performing an in-order traversal just naturally gives you a sorted list of everything in the tree. And we saw how its typical O-log-n efficiency makes it much faster than simple arrays for searching and removing data.
Mm-hmm. And we also hit on that really crucial caveat. All that great O-log-n speed depends on the tree staying reasonably balanced. We saw the risk of performance completely degrading to O(n) if the tree gets skewed and turns into something resembling a linked list.
It really is a fundamental data structure in computer science. Understanding its principles, its strengths, and that key weakness gives you a much deeper appreciation for how data gets managed efficiently under the hood.
You know, this actually raises a really important practical question, doesn't it? If a standard basic BST has this risk of becoming unbalanced and losing all its efficiency, how do real-world applications that rely on these kinds of ordered tree structures actually handle that? How do they ensure they stay balanced over time, even if users are constantly inserting and deleting data in weird patterns? Are there like more complex variations of BSTs out there that are specifically designed to automatically prevent that degradation? Maybe ones that rebalance themselves somehow?
It's a fantastic question to leave folks with. What comes after the basic BST? A great thought to mull over. Thanks for joining us on this deep dive into binary search trees.